Yes, thank you, Sarmistha. Topic of my talk is quark matter and compact star. Pretty simple as it sounds, but it's not that simple, of course. Okay. So I made up a little battle plan for this presentation. I hope I can stick to it. I am ready to cancel the talk somewhere in between. So if I'm running out of time, just let me know in advance. What I want to speak about is QCD. Why is it important to look at QCD in compact stars? Why is it actually relevant? Why would we and how can we do it? The tool that I like to apply is the Dyson-Schwinger approach. So Dyson-Schwinger approach is an approach which actually bases on the QCD action, which we can evaluate, of course, within some approximations. But these approximations are already meaningful. They tell us something. One of the things I want to notice so I will speak about distribution functions and a bit about the equation of state, but not so much. And that is just in the beginning to illustrate what one can expect from a framework which is QCD based and not a mean field model as we would usually do it. So I will speak about non-local interaction models. I will speak about the NJL model, which is a contact interaction model. So it's just local interaction. I will speak about the Back model as an effective model, and about a clone between one and the other. So a hybrid between NJL type and Back models, which is VIII. And that is just the proud of the father. So I will speak about a model that I developed when I was in Poland. Since just speaking about the equation of state can be a bit dry, in particular for a, let's say, undergraduate, early PhD student who is not in the field, that might be a bit overwhelming. So I want to speak about some applications. So what do we use with, what do we do with that? So does quark matter actually matter? The first point I want to illustrate is that, yeah, actually we can use it to constrain the equation of state or to learn something, for instance, about symmetric matter as we find it in heavy ion collisions. The other interesting aspect is related to supernovae. So we can explain something, maybe, just by the existence of quark matter. That is an interesting paper which was written when I was still in Poland, so my previous spot. And the last thing I speak about are some remarks about the strange matter hypothesis within that framework. Okay, so much about my battle plan. I hope I can stick to it. So these are the typical scenarios that we know so in this context here of CSQCD, compact stars in QCD, most of you will be familiar with that. So there are different ideas what a neutron star could look like. It could be made of pure nuclear matter. There could be an inner core made from quarks, or the most exotic model that we know about is a strange star, so consisting almost entirely of strange quark matter. And all of these models are justified somehow. It's not like they are completely made up. And that's the question. So neutron stars, do they have a quark core? Are they made from one or the other? And what we want to have in the end, of course, is a smoking gun for one of these hypotheses. So is it possible to have just a core? Is it possible to have strange stars? Or is it just a fancy idea? And as long as we don't know that, we have actually a very nice playground for theoretical physicists. I will make a remark about that picture in the end as well. But for now, yeah, let's just have fun and play with the models that we have, but try to be serious as possible so that nobody gets hurt. So what's so special about quarks? There are two things about quarks which are remarkable. One is confinement, which in a very simple way means that no isolated quark has ever been observed. If you look around the world, at the world around us, there is nothing like a free quark. So quarks are confined and we find them in baryons and mesons, but that's what it is. So they are constituent particles. Nevertheless, at large density, large temperature, we would expect that there is a phase transition to a quark-gluon plasma. The other remarkable thing, which is some models forget about it, some don't, is a very particular feature, which is the dynamic generation of mass at a large scale. So if you look at the proton with almost 1 GeV mass and the constituent quark mass of light quarks, which is of the order of 5 MeV, you see that there's a discrepancy. So 98.4% roughly come from somewhere, but we know that this is not somewhere. We know that this comes due to the interaction of quarks via gluon exchange, which we want to take into account in one way or the other. Another interesting thing is that the process of gaining mass depends actually in which environment the quark lives. Yeah, in a proton, you have 940 MeV divided by 3 quarks, which is a constituent mass of 300 MeV. In a pion, it looks a bit different. So here you have a mass of 140 MeV, you have 2 constituent quarks, quark and antiquark, and you end up with a mass of 70 MeV. It's a point which I won't address much in this talk, but it's something remarkable. So this is a non-trivial feature. Yes, so structure matters. Yeah, so this effect of dynamic chiral symmetry breaking is a key feature of QCD that we actually want to preserve. And another remarkable thing about that, it's a distinctly non-perturbative feature. What does that mean? It means that in a perturbative model, if you start with a bare quark mass of 0, which you could think is a good approximation for a light quark, you wouldn't be able to gain any mass out of that model. So you need at least a bit of seed mass to describe something which looks like chiral symmetry breaking, but still you wouldn't get the non-dynamic, the non-linear character of that thing. That's not how it works in a non-perturbative treatment. In a non-perturbative treatment, actually you can ignore the bare quark mass. You can set a light quark to a mass of 0 and you still would be able to describe a dynamical quark mass which is non-zero. But for that you need a non-perturbative treatment. So the idea, of course, would be to have a framework which works with both. That you have chiral symmetry breaking taken into account and you have a confining model. Reality for many applications in astrophysics is that we use either Bagchi models or NJL models or completely phenomenological models. There is not much else around. So the distinction between Bagchi model and NJL model can be put in a very brief way like that. Bagchi models have actually been developed to take confinement into account. The original Bagchi model has been developed in order to describe hadron masses. What we are using in astrophysics is a thermodynamical extension of this model, but the origin of the Bagchi model is that it takes confinement into account. And the price that has been paid at the time it has been developed, which was in 1974, is that chiral symmetry breaking is completely ignored. So when you speak about Bagchi model, you speak about a model with constant constituent quark mass. It's not dynamical. In the NJL model, it's a bit the opposite. NJL model has been explicitly applied because it has chiral symmetry breaking in it. And the drawback of the NJL model is that in the original form, it has no confinement at all. Nowadays, you can apply some extensions, Polyakov loop. But even then, it's not entirely satisfying. So if you increase the temperature just a tiny bit, you will always have some residual quark number densities, even in a very low density state. So it's not perfect yet. But for both model holds, they are inspired by QCD, but they are not QCD. So you never start with a QCD Lagrangian. It's not what you do here. Lattice QCD has problems at t equals 0 and finite chemical potential, finite density. So these are not yet solved. And the framework that I really like to apply is the Dyson-Schwinger approach. The idea here is that you derive gap equations from the QCD action. So basically, yeah. What you get out of that is a set of equations which relates the self-energy, so the dynamical properties, the in-medium properties, to the propagator of that particle, interactions of that particle with each other. That approach has been very successfully applied in vacuum at 0 temperature, at finite temperature as well, to describe meson and baryon properties. So meson and baryon masses can be described very well within that approach. And what I want to show here is how it can be extended from vacuum to finite density. So this is nothing entirely new, but it's interesting. And the hope, of course, is that we get an equation of state which actually is derived from the QCD action, so that you start from a solid ground. So you know, this is my partition function. I derive my gap equations from that. Of course, if one could solve that exactly, it would be the exact theory. That's not possible. One has to make some approximations, but at least you know which approximations you make. And you can work on that. Another illustration here that is exactly dynamical symmetry breaking. So the illustration that I'm showing here is a comparison of Dyson-Schwinger results with lattice results. And you see that they are in remarkable agreement. Yeah, one thing, the red curve here with m equals 0, that's the chiral limit. That's what I mentioned before. So you are able to acquire dynamical mass in a model which starts from 0 bare quark mass. And that is an effect of the non-perturbative treatment of interactions in this model. In comparison, the back model has a bare quark mass at all momenta and density. That means here that's a scale of GeV, 100 GeV. So the bare quark, so the mass in the back model is somewhere here. In the NJL model, you have a dress quark mass at all momenta, but it changes dynamically with density or temperature as you wish. Yeah, but here that's momentum dependence. That means in the NJL model, you have something like just a line here, and then you would drop it at some point to 0 value, or you introduce a cutoff in order to not be in trouble when it comes to thermodynamics. However, it's a very different behavior, and the question is, does it do something? Is it important actually to have that momentum dependence in there? And that's what I want to discuss now. So just briefly how it looks like, what you get in the end, and I skipped many parts here of the approach. What you get in the end is what we call a gap equation. So you have the inverse propagator, and this is defined by a free particle propagator. That would be the first part here. That I mu here is the extension which you have to apply if you want to take finite chemical potential into account. And if you would start your theory, calculate thermodynamical properties from this, you would just get a free Fermi gas. So this is what it does in the end. However, there are self-energy terms. And these self-energy terms, of course, play the important role here. And that's the entry point for simplifications. Here, it's getting complicated very fast. Why is it complicated? So the structure of the self-energy would be something like you have a quark. That's the quark line. You have a gluon, which is emitted, it's absorbed. And the gluon itself actually is a dynamical being too. So the gluon itself is coupled again to the quark. And the interaction, the vertex here, is non-trivial in character as well. So you have to apply some simplifications already at that level. You can, of course, make it more complicated, but in medium, this is what we do. So one approximation you can do is that you say, okay, I do not care about the finite structure of the dressed quark gluon vertex. I just replace it by a free quark gluon vertex. And for the quark propagator, for the gluon propagator, I can say, okay, let's say in terms of structure, it's still the free gluon. However, there must be some additional momentum dependence, and that we can model. So you make an ansatz for the effective coupling. And what you do then as the next thing is, if you look at the Dirac structure of the propagator, and if you look at the Dirac structure of the self-energy, it's perfectly the same. So these gammas, gamma 4, gamma 1, 2, 3, here you have a scalar term that works kind of a coordinate system, or like base vectors in the coordinate system. So all that self-energy can do is it can change your place within that coordinate system as a function of momentum, as a function of density, as ever you wish, but it cannot change the structure that you see here. So there will always be a term with a gamma vector p, there will always be a term with a gamma 4, and there will always be a scalar term. So the general solution of this one looks perfectly like this. It's exactly the free structure, but you have a gap function here. That's at A. You have the same structure as for the free propagator, but you have another gap function, which we call C. And you have a scalar term, which replaces the mass. So this would be the effective mass of the particle, modulo some corrections. I mentioned that because I will show some of these A, B's, and C's. So I want you to remember where it comes from. And then in the next step, oh, something went wrong here. That doesn't look nice. So that is supposed to be a vector sign, I guess. That went wrong. Now we look at the self-energy. For the self-energy, we say we replace the dressed quark-gluon vertex by the free quark-gluon vertex, which has this structure, and the full dressed gluon propagator by the free gluon propagator, and some effective coupling. And that behavior of the effective coupling that you have to specify. The way it's done is you make a more or less educated guess, and then you try to fit it, yeah, to mass vector of mesons, hadrons, and so on. And that technique is well understood in vacuum and widely applied. There are, of course, other ways to do it, but this is one of them. And here one has typically three terms. So the first one is a delta function. The delta function is kind of important, but what actually is important is that you have an infrared enhanced quark gluon propagator. Infrared enhanced because this is what we connect to confinement. So confinement happens in the infrared. The second term is actually something very similar to the first term. It's a soft inversion of a delta function. So you see that exponential here. And then we have that long range behavior, large K running coupling. So this is in order to reproduce asymptotic behavior of QCD. And now you can start playing with this ansatz here and just look at what different terms do. And this is what I want to do. So I will show you one result, first term. That model has been investigated already in 1983. So it's quite a while ago. Where you just take that delta function into account and see what happens. In another approach, you can just look at that second term. You will notice that I never take all the terms into account. And remarkably, actually, you can reproduce the NJL model perfectly within that approach by assuming that that effective coupling here is just a constant. Yeah, so you just turn that into a constant, which makes sense. So this is the Fourier transform. If you have a contact interaction and you take the Fourier transform of a delta function, you get a constant. Yeah. Okay, so for the Munchik model, as I said, that would be the first part, the delta function. That has one wonderful effect, and the wonderful effect is that if you look at that integral and you plug in a delta function, that integral breaks down. So you actually don't have to perform any integrations. You get an algebraic equation, which you can solve. If you set the bare mass to 0, you can actually solve it analytically pretty easy. And you can do that in medium, and you get the solutions for the gap, and one realizes that there are different solutions, and that makes perfect sense. So there is a massive solution and a massless solution. Let's look at the massless solution first. So in the chiral limit, that B, which was the scalar gap, that just drops to 0. That A and C gap are the same, which is always the case in that model. And you have a particular structure for that C, which I don't want to show, but there is the analytic solution. There's a Nambu phase where you actually have a massive solution, and that C gap turns into a constant. If you have that information, you actually can start to do thermodynamics. So given these gaps, you can start to calculate the distribution function, which is defined in this way. And here you see the propagator appearing. You evaluate that integral. And then you see some interesting behavior. So for a free Fermi gas, of course, at t equals 0, we would expect you have just the typical Heaviside step function behavior, where the distribution function drops from 1 to 0 exactly at the chemical potential. But this is not what's happening in this model. So here you see some domain where you're coming down from 1 to 0. The width of that region is defined by the coupling strength, which is applied in that model. An interesting effect is if you go to very small density, very small chemical potential, actually the coupling is the dominating effect. So what you do is with increasing potential, you start to build up something which looks not at all like a distribution function as we know it in the beginning. And only if you reach a certain critical value, you start to reproduce something which looks like a Fermi distribution function, but you always will have that soft edge. It's just that at very large density, that region is comparably small compared to the solid Fermi sphere. And that's what we see if you look at the thermodynamics. So if you think of this one and you integrate over it, you get something which does not have exactly the dependence on chemical potential for the pressure as you would expect it for an ideal gas. So for an ideal gas, it's mu to the fourth. So here actually it grows with mu to the fifth because it grows in 2 dimensions. Yeah. So it does not just, it's not just the step function going from left to right, but you have a sphere filling up. And that gives you a mu to the fifth behavior. It's a very different behavior. Let's go on. If you take that second term into account, you get something unexpected, actually, if you look at the results from before. So this is essentially a soft inversion of the delta function, but what you see is a state which is not fully occupied neither. So here you see a distribution function which has occupied states up to 0.9. So probability that there is still room to do things. And that might be really important. It might be important to look into this more carefully. And I'm not aware that someone actually did it, because transport properties are defined by terms which are typically products of the Fermi functions with each other. So distribution functions play a big role. So here, actually, you can have some dynamics going on. Typically, for the ideal Fermi gas, you say everything happens on the surface of the Fermi sphere because the Fermi sphere is filled up. This is not true in this, and it's not entirely true in this case. Yeah, so momentum dependence of the interaction plays a crucial role for the distribution function. And that's the only statement that I really want to put out here because I find it valuable. So now let's speak about the NJL model. NJL model, as I said, you just take a constant for the effective gluon coupling. You do the same approximations as before, and you end up with a set of equations. You see again, gaps A, gap B, gap C. You can massage that a bit, and what you end up with is that you realize that A has to be 1. That has to do with the fact that here you have momentum, external momentum, internal momentum. Whatever you do with that integral, for every q that you will find a negative q, and everything compensates each other. And the only thing that's left in the end is just that p squared. So that leads us to understand that A has to be equal 1. For the mass gap B, we reproduce something which depends on the bare mass and here on the scalar density. That looks very familiar. It's very, very similar to what we know from the actual NJL model. Actually, it's perfectly the same. And you can do the same for the vector gap, C. Here you have to massage a bit to realize where you actually find the gap. So what is my mu, what is my mu star? But you can do that, and you get perfectly the gap equation, which you would expect from the NJL model as well. So there is a one-to-one correlation. You perfectly understand Dyson-Schwinger equations and NJL model. That is 2 sides of the same model, and we understand which approximations have to be made. So it's rainbow approximation, and it's a contact interaction, which is not so surprising. So starting from there, one can derive the thermodynamical potential, and the message I want to shorten a bit here is essentially perfectly the same. You get a free Fermi gas behavior in one term, and you get an interaction term, and that goes again with exactly these gaps. So, which is this part and that part. It's perfectly equivalent to the NJL model in the simplest version, of course. So I have no superconductivity taken into account here. So it's really a simple case, but the analogy is definitely there. So NJL model is really a particular approximation within QCD's gap equations, and probably not a particularly, let's say, advanced one. So we killed all momentum dependence of the mass gap solution, for instance, which is a clear difference to what we had for the Mooncheck model. There's momentum dependence. It's a clear difference to the momentum, to the broadened delta function. So these models all have some kind of momentum dependence for their mass gaps. The NJL model does not. I skip over that. I skip over that because the statement is the same. So now I want to speak about back model from the NJL model perspective. So what I'm showing here is the mass skip solution as you would get it within the NJL model for light quarks. So that's what you would typically get. It's that line. Here you have multiple solutions, so you have to figure out at which point you go from this branch to this branch. That you would typically do by calculating the pressure, looking for the maximum in order to minimize the thermodynamical potential, and then you see that there is really a first order phase transition going from a massive to an almost massless solution. At the same time, you can calculate the pressure. The pressure in the NJL model would behave like this. It's 0, 0, 0, 0, 0, 0, 0. Then you have the transition domain here. And then it goes up. And that here is some numerical dirt, which has to do with the fact that you have to introduce a cutoff in order to not have the NJL model diverge. Although at this point, you don't need it. But you see that behavior here. The blue line, that is just the ideal gas. This is what you would do within a back model. The interesting thing is, if you're familiar with the back model, you get a back constant here for free. It just comes. I see that there are...
Sorry, you can answer the question later. So just type it.
Okay.
You can answer them later.
Okay, so I click it away for now. So you see that there actually is something like a back constant, but the interesting thing about that is the back constant in the original back model has been introduced in order to mimic confinement. There is nothing like dynamical chiral symmetry breaking. Quarks have a fixed mass. So the back constant in the thermodynamic back model, as known, is really attributed to confinement. That's not the case here. So here you have a back constant which is actually attributed to chiral symmetry breaking. It's the dynamical generation of mass, which plays a role here. You can repeat, oops, now let's see. You can repeat the same story for the strange quark and you come up with the same conclusion, although the window is a bit tinier, but the behavior near the transition point is still perfect, almost perfectly that of a free Fermi gas. Modulus and back constant. So the only effect that all the noble treatment of dynamical chiral symmetry breaking that we put into the NJL model has in terms of the back model is that we have a shift here. And that is enough to describe the deconfined part. So the part where chiral symmetry is restored in very good approximation. And that raises a kind of awkward situation. So why is it awkward? Well, if we construct a phase transition from nuclear to quark matter, typically the assumption is we have a quark matter model, we have a nuclear matter model, and then at some point we switch from one to the other. So now we have an informed model, NJL. NJL tells us something about chiral symmetry breaking and chiral symmetry restoration. If we take that model serious, it would tell us that the transition from massive quarks, constituent quarks, to more or less massless quarks happens at a given chemical potential, and that would be here. The phase transition from nuclear to quark matter would happen when the pressure of both phases is equal. So the TM1 here, that's a relativistic mean field model for nuclear matter. So you increase the pressure, you increase the density for the nuclear matter part, you increase the density for the quark matter part, and you see at some point they will cross, and that's what we would typically assume is the deconfinement chemical potential. So what's the awkward situation? The awkward situation is that within that window here, we are assuming that we have a nuclear equation of state, which is based on nucleon masses as we know it. But at the same time, we assume that chiral symmetry for quarks is restored. So the dressed quark mass within the nucleon actually is decreasing, and it decreases drastically. It's not really consistent. A solution to that dilemma is to say, okay, we actually can lift this one. And we would have to lift it by an amount which is this one. And that is related to confinement or deconfinement, if you wish so. So we have a back constant, and that's this curve now, yeah, where we've done exactly this. So you have a back constant, which is an effective back constant. That's this value, or here it's yellow. And that has two contributions. So one comes due to chiral symmetry breaking, and it's a large value. And NJL models are known for that large value. But then you reduce it if you go into deconfinement. And that's the thing that we actually understand. If you look at bound states always have less energy than the energy of the total system of constituent particles if they would not be bound. And that's very similar to what we propose here. Another advantage is if you look at the back model from an NJL model perspective is that you can take vector interaction into account. That usually is not done before, but actually it's very simple to incorporate that. So the effect of vector interaction just comes here. So you have a renormalization of the chemical potential, and what that does in the end is that you stiffen the equation of state. If you stiffen the equation of state, that means you flatten the curve of pressure versus chemical potential. And this is illustrated here. Yeah, so without vector interaction, that would be standard back model. Your curve looks like that, and now you can turn on vector repulsion, and you make your equation of state stiffer. And that's a nice feature because we know that we know stiffness in order to achieve large neutron star masses, for instance. So basically, that's what the VIII model would be about. It's essentially just a back model. So you have here a free Fermi part. You have a back constant. However, that back constant now can be flavor dependent. And on top of that, you have a vector interaction kernel. So that is the new part. So this is what makes VIII. That's what makes the difference to the standard thermodynamical back model. Except for the fact that actually the chiral back constant here, that is flavor dependent as well. And if you sum over all particle species, yeah, that I stands here for up, down, strange. If you sum over all of that, then you end up with a model which looks perfectly like the back model. So you have here your kinetic part and you have an effective back constant. However, that effective back constant, as said before, it has a chiral part, and then you subtract the binding energy. So. And we can look how that works if you do neutron star calculations. This is just playing around, but one remarkable difference to the back model, of course, now you can have different chiral back constants for the light quarks and the heavy quarks. So for up and down, and for the strange quarks can restore chiral symmetry at a higher chemical potential. So you can have a phase where you actually have light quarks, but still an S quark, which would be dynamically dressed. The other thing that one can do is one can look at what does that vector coupling do, and this is the nice part about it, or a nice part about it. So without vector coupling, you can try to get massive neutron stars, so that 2 solar masses is roughly what we want to get. But if you're unlucky with your parameterization, you end up in an unstable branch. So basically you have a nuclear, a pure neutron star, and as soon as the phase transition sets in, yes, that can happen, but the neutron star straight renders unstable, and this is not what we really would like to see or investigate. That would basically say, okay, there's nothing like Quark, at least not in this model. So if you turn on vector repulsion, it's not a big surprise that it works like that, but it's nice to see that it actually does. Then you stiffen the equation of state, you can acquire higher masses, and the stronger the vector coupling gets, the higher the mass becomes. So that solves some issues. Okay, so that would be conclusions, but I'm running almost out of time and I wanted to explain a few things. So you can use that to adjust the quark matter equation of state. Now we have more parameters available, but this is rather standard for NJL models. So I will jump over that a bit too. Yeah, I just go over this part. So maybe an interesting consequence of a phase transition to quark matter might be that it can explain why massive stars, which have been observed to explode in a core collapse supernova, leave a remnant, and that remnant actually might be a massive neutron star. So there was a paper by a collaborator of mine. It was mainly the work was done by Tobias Fischer, and it's a while ago already, where he looked exactly in that problem. So what happens if we have a phase transition to quark matter? within a supernova. And at that time, he predicted that there would be a second neutrino oscillation. So basically, you have two shock waves. You have, once this supernova sets in, star falls together, you form a shock wave, and typically that's it. So now you have two options. Either you form a neutron star or you don't, and the thing falls together into a black hole. If you have a phase transition, actually you can have a different situation. Matter falls, you get a first shock wave. However, matter can now, under the phase transition, absorb more energy, and you stall a bit of that falling together of matter into the core. So at some point, however, phase transition is over. It's like boiling water, basically. So once there's enough energy, then you go on that quark matter branch, and you trigger a second shock wave. Yeah, you compress it once, then you hit that point of phase transition, you absorb energy into the phase transition, and once that is done, you have a second shock wave. And that second shock wave can come with a neutrino signal. So if there is a delayed neutrino signal, or if there are two delayed neutrino signals with some subtleties, that might be an indicator for the existence of quark matter. At that time, the problem was that my colleagues used an equation of state which was not particularly stiff. So they had maximum masses which have been not in good agreement with observations. But that has been fixed later. And the interesting result of that was that we applied that idea to very massive stars, and that massive stars are supposed to fall into a black hole. That's what simulations showed up to that point. However, so that would be the standard situation. So you have a neutron star with 12 solar masses, no phase transition, nuclear matter. Supernova goes on, and you move your star through the phase diagram. Yeah, so you increase density, you increase temperature, entropy is more or less constant on that path. If your star is not too massive, you will generate a neutron star. If it's very massive, however, you go through that phase transition domain, which in that case doesn't exist. So you increase density and density and density, and mass falls on it, and the whole thing just collapses. So black hole formation. Okay. You increase the density to insane amounts, nothing interesting happens. And interestingly, if you assume that there is a phase transition, you can generate scenarios. That doesn't mean that that is the scenario, but it is a possibility. If you go through that phase transition domain, several things happen, but the main effect is exactly the one that I just explained. So you have that stalling, yeah, of the infall of matter. So the compression doesn't work as fast as you would expect, and you actually are able to generate a neutron star, which is a hybrid star. It has a quark matter core, and this is basically illustrated here. So you end up with a mass of about 2 solar masses, and that is a neat feature because it really explains where that heavy guys could come from. So these could be the remnants of supermassive blue giants. A last thing I want to speak about is strange matter. About strange matter, one has to know 3 papers actually. Then you're pretty much informed what is the idea behind it. So the first one you have to look into would be the Bagch model, the original Bagch model, the MIT Bagch model, which has confinement in it. The second one was a hypothesis by VIII. He came up with it about 10 years after the Bagch model, and he basically observed that if you compare the energetic content of 2-flavor and 3-flavor matter, 3-flavor matter has less energy per baryon, per particle, than 2-flavor matter. So why is it interesting? If you have 2-flavor matter, that's actually what neutrons and protons around us are made from. So you would expect that a bound state of these light quarks, that should have less mass because there's binding. However, if the energy per particle of 3-flavor matter can be even less, then you might have a state where strange matter is more stable than nuclear matter, and nuclear matter is still more stable than 2-flavor matter. So, which means strange matter could be the most stable state of matter that exists. The question is how to get there, how to get into that state. except for waiting for infinity. So because the transition rate might be pretty slow. And that idea has been picked up pretty much in the same year. That's 84. So that was summer, that was December. And it has been picked up by applying exactly the back model, the thermodynamic back model, in order to investigate that idea. And there have been made a number of assumptions. And these assumptions are important to understand where the stable strange matter hypothesis comes from and where the limitations might be. So first assumption, it's a limiting case of the original MIT back model. It's not actually the MIT back model. What you're doing is you take that back and you forget about all the fine structure that's in there in the original back model, where one really looks into boundary conditions and so on. So here it's really that you say, I have an energetic back, I fill it with quark after quark after quark, and at some point, of course, you should have something like a free Fermi gas. However, there is still that confining background field, and that is the back constant. The other assumption is that chiral symmetry is restored within the back model, which means you're using bare quark masses. You have no dynamical breaking of chiral symmetry. It's just not incorporated. And the next part, which is not so important here, says that perturbation theory is applicable. So this affects correction terms to the back model, which I completely ignored during that presentation. However, if there is a point where perturbation theory is not applicable, it's actually the transition from confined to deconfined, or the chiral phase transition. So wherever you have a phase transition, perturbation theory is not really the best thing to do. And then they started looking. So this would be the energy per particle, 859, 879, 899, 919, 939, and this would be something like iron, nickel. So these are the most stable elements that we know. And that as a function of the back constant and as a function of the constituent quark mass, which you're using, or here it's the strange quark mass, which you're plugging into your model, and you can apply your perturbative corrections. So if you're on that side of the plot, strange matter wouldn't be more stable than nuclear matter. If you're on that side of the plot, it would be more stable. That's basically what this one wants to tell us. If we look at an NGL model, in an NGL model, everything is fine or not. So in the NGL model, typically you say there is no stable strange matter. And the reason for that is that the back constant in the NGL model is pretty large. However, if you do that modification and say that actually I want to have agreement of chiral phase transition and deconfinement phase transition at the same chemical potential, and the chemical potential where it happens is the chiral phase transition chemical potential, then you have to reduce the effective, back constant, and you get an effective back constant, and that actually is within that domain. So question, what do we have now? Is it, as NGL predicts, stable? Or is it, if I reduce that whole thing, unstable? Opposite, sorry. Is it unstable, or is strange matter stable? And the answer, I'm not completely done with the answer, but my assumption is it's most likely not a question. And the reason for that is that, of course, we have dynamical chiral symmetry breaking. So if you make that assumption, if you make the comparison of a back model with nuclear matter, and you assume that your quarks are chirally restored, so symmetry is restored, that means you have light quarks, no dressing, then of course you have less energy content. However, if you increase the mass, and that's what the NGL model tells you, if you increase the mass, that means you increase the energy per particle, and that energy per particle actually should be higher than that of nuclear matter. And that's what this plot is supposed to say. So this here is the transition density or chemical potential where chiral symmetry breaking is happening. And now you can plot energy per particle for 3 flavor matter and for 2 flavor matter. So 3 flavor matter, I just realized here by saying that at low density, I just have 2 flavors. The 3rd flavor comes in here. 3 flavor, I realized by just setting the back constant for the flavor-dependent back constant for the strange quark to 0. So that is strange matter. Yeah, black is strange matter, red is 2 flavor matter, and you see that gap. And the name of the game now is to move that curve into an area where you end up with a situation where the minimum is that curve, so it terminates exactly in the minimum, where the minimum is at a point where you're beyond that 939 line. So 939 is exactly here, and you see there's a case where this never happens. Here's a case where it actually did happen. So somewhere in between, you have exactly that scenario that you can have unstable two-flavor matter, stable three-flavor matter, stable strange matter. However, that is all in the domain of dynamical chiral symmetry breaking. And as soon as you're in that domain, you cannot work with a bare quark anymore. You actually have to take a dress quark into account. But then the discussion is over. So then there's not much you can do anymore. You see that here in that domain, and that was an extreme case that we chose already, you are far beyond that. So of course there are ways to fix it. So you can now play with the onset of chiral symmetry breaking. Yeah, does it have to happen in this domain, or can we shift it a bit to the left so that it actually might work? That's why I'm not done with the answer. However, the existence of stable strange matter is not that easy to predict, and the pure back model, so a model without chiral symmetry breaking in it, is probably not the proper tool to address that question. And that's the exclamation mark which I want to raise. However, and that comment should be made too, probably the NJL model is not the right tool to answer that question neither. Reason for that is that you have a that NJL model has no actual confinement in it, and that plays certainly a role if you want to fix the back constant, an effective back constant. Okay, and I think I am pretty much in time, right? So I would end it here. Conclusions. It would be nice to actually understand QCD if you want to say something about QCD in compact stars. However, the problem is really complicated. So it's not trivial, and but nevertheless, that should be the goal. So NGL and back model one can understand kind of in a QCD framework, and we understand where the shortcomings are. And actually we see where we could improve. Where that leads, I don't know yet. However, non-local interactions certainly play a role, so should be taken more serious. And the consequences can be rich. First of all, of course, we can support the search for the critical endpoint, because actually we can use our equations of state, and we can more and more adjust them to observations from neutron star physics or gravitational mergers and whatever comes up. If we have a model which describes QCD, if it's a good theoretical model, it should work over the whole phase diagram and not just down there in our area, but it should work up to heavy ion collisions as well. So proto-neutron star evolution seems to be an interesting topic. Supernovae, I mentioned. Strange matter, still not entirely clear. I find it a bit less likely than I don't know, 10 years ago, but still it's a possibility which really needs to be observed. The other thing that I want to mention again, that interesting behavior of distribution functions in a more QCD-based approach, that can have rich consequences because it affects transport, and transport seems to be extremely important if you want to speak about the dynamical behavior of astrophysical objects. G-mode oscillations, I did not mention at all. I hope that Prashanth will do so. And there's lots and lots of work to do, and at all ends. So equation of state, really, I think if we want to make progress, in particular in the compact stars and QCD framework, we have to pay closer attention to what QCD actually wants to tell us. Phenomenology, we are getting lots of data, and transport is a topic which is addressed, but often in a quasi-particle approach, where dynamical properties, so momentum dependent mass gaps and stuff like that, don't really play a role. And in the end, of course, you want to plug all of that into very complex simulations. So to convince people to actually use more advanced equations of state, it's hard work. And I understand that it's hard work, and I understand a certain resistance on the side of modelers as well, because it really is not always trivial to put it in there. However, coming back to that picture that I showed initially with the playful guy, I think we are slowly leaving that stage. So maybe the next thing we could look for is not a toy gun, but something like bow and arrows. So it might be the right time to choose our weaponry a bit more carefully and not to play around as much as we used to. Okay, that would be it. Thank you, and I will look for questions, or maybe I don't know, how does it work with questions? Should I read the chat, or is someone actually talking to me? Am I still online?
Yeah.
Okay.
Thanks, Thomas, for the wonderful talk. So we have a few questions. So first one is from Prashanth. What physics do you get at next order in the expansion of the coupling answers in the gap equation?
What physics you get?
Yes, at next order in the expansion of the coupling answers in the gap equation.
So that depends in which direction you're looking. So of course, if you're looking in the asymptotic domain of QCD, you would hope that your results are getting more and more correct. So I think the closer you get to the phase transition, the larger your error bars will turn, and the question what you get, I cannot tell you. So that really is the way to answer that actually would be to solve QCD exactly in that domain and to compare it to perturbative QCD. But I don't think that you can expect convergence in that area or meaningful results. Nevertheless, it's an extremely valuable guidance. Yeah, so to know the asymptotic limit of your model is extremely valuable. But that's what it is. It's the asymptotic behavior. So, and yeah, so to put it short, you probably decrease the area of uncertainty. So the good thing about doing perturbation theory to a higher and higher order is that you're probably able to shoot into the right solution earlier with a model which is based on an effective ansatz, like we have it with that model, but which has perturbative features of QCD in it. So it's easier to come to agreement.
Okay. Prashanth, you want to add to anything?
No, we can go ahead.
Okay. So next there is a comment from Debarati Chatterjee. QCD induced phase transition in core collapse supernova has recently been confirmed by simulation from Ivan O'Connor group at Stockholm University. So it's just probably in connection with what you said.
So, okay. Confirmed is a big word for a simulation.
Okay.
And is the term maybe investigated? Because that's what we did basically too. So that really is, so the thing about the phase transition to QC to quark matter is that it's model dependent. So we don't have a good quark matter equation of state. We just don't really know, unless there is a really hot smoking gun. And I'm not aware of this, but I would be grateful for the reference. Actually, I think I missed it.
So I have one question. So you are considering only quark matter. Do you also consider the this superconducting quark matter and the CFL or something like that?
Yeah, so in terms of NJL model, we do that. In terms of the simplified models, not yet. So that might be a next step, next valuable thing to do. So for NJL models, this is common. So many people do that, and it has been investigated. Phase structure is rich and interesting. So it's certainly a topic which is worth to look into.
Okay.
And fun, yeah.
Yeah.
Okay, so
then, we thank the speaker